Linear programming or optimization. Linear programming is a mathematical technique for finding the best uses of an organization's resources. In short, we make use of LP for linear programming. Take note, linear programming composed of two words. We have linear and programming. The word linear is used to describe a relationship between two or more variables, a relationship which is directly and precisely proportional. In algebra, our common variable that we use is x or y. Okay? And then for programming, this refers to the use of certain mathematical technique to get the best possible solution to a problem involving limited resources. So take note that linear programming, this is more on how we use the resources in an organization. In an optimization problem, the objective is to optimize or max. If we say optimize, we're speaking of maximize or minimize some function of f. So we make use of f here as our function. Our objective is to maximize or minimize. That depends on the problem. Linear programming or linear optimization consists of methods of solving optimization problems with constraints. Okay, now we will proceed to page 2. We have the applications of linear programming. All organizations have to make decisions about how to allocate the resources, which means we have our definitions of linear programming. We're talking about optimization or maximize or minimize our resources in an organizations. And there is no organization which operates permanently with unlimited resources. Consequently, management must continually allocate scarce resources to achieve the organization's goals, whatever they might be, and organizations can have many goals. So definitely, we know that in an organization, there is no limited, there is unlimited resources. I mean, no organizations operates permanently with unlimited resources. Now we have here our examples in the application of linear programming. A bank wants to allocate its funds to achieve the highest possible return. It must operate within the liquidity limits set by regulatory agencies, and it must maintain sufficient flexibility to meet the loan demands of its customers. So very clear for this part is in our example, uh, a bank wants to allocate its funds in order to meet the loan demands of its customer. Another example for in the application of linear programming is an advertising agency wants to achieve the best possible exposure for its client's product at the lowest possible advertising. We have four basic components of linear programming. We have decision variables, which represents quantities to be determined. Another one is the objective functions. This represents how the decision variables affect the cost or value to be optimized. Constraints, it represents how the decision variables use resources which are available in limited quantities. And lastly, we have the non-negativity constraints or the data which quantifies the relationship represented in the objective functions and the constraints. So, suppose we have our example. Let's say we want to maximize the profit for, let's say we want to produce tables and chair. We have a certain company wants to produce a tables and chairs with a maximum profit. So each decision variables we will make use of x and y as representation of our tables and chairs. Okay, so let's say our x here represents tables, and then we will make use the variable y as a chair. Okay, And then the objective functions here represents how the decision variables affect the cost or value to be optimized. What this means that uh, we're going to make, again, this is a function. So let's say profit in producing tables and chair. Let's say P stands for the profit, which is equivalent to, let's say, 2 times X, which is the unknown variable for numbers of chairs, I mean table to produce, plus 3Y. Okay, this 2 here is the amount, let's say, in pesos or in dollars. So in peso, let's say, we will change this one into, let's say, 20 pesos. Okay, or 30 pesos. Okay, this 20 pesos assumes the cost of the table when we produce a table, and this 30 pesos assumes the cost of chair when there is a production of chair. So let me change this one. Okay, so we have here, this is just an example of how we write our objective functions. And then for the constraints, for example, we have our example for constraints. Let's say 2x plus 4y, we have less than or greater than 40, and then 3x minus 2y less than or greater than 30. So these are just an example of how we write our constraints. And then of course the non-negativity constraints, or the data, is composed of your variable, let's say x and y, which must be greater than or equal to, if you want to produce your x and y, so it must be greater than or equal to 0, and then this one is also equivalent to 0. So these are just an example of how we write our non-negativity constraints, or the data. So take note that the components of linear programming, we have here our first decision variables. We have to make use of any variables you can do. So we have this one, and then for the objective functions, we have this one as our example, and then the constraints, we have this one as our example for constraints, and then the non-negativity constraints, we have this one as our example. Later on, if I going to present to you an example, then we will write in this manner. Okay. Now, in linear programming, we have different methods to solve the problem. One method is a graphical method in linear programming. This is an example of how we present our graph in a graphical method. For example, this one, we have here a line and then another line here. And then this area, we call it as our visible region. Visible region. This is the region wherein the maximum or minimum points from this graph is going to determine. This visible region is a solution space, or we call it search space. This is the set of all possible points of an optimization problem that satisfy the problem's constraints, potentially including inequalities, equalities, and integer constraints. So, for example, this one, point 1, point 2, point 3, and point 4, we identify our point for this part at 0, 0, we have this one, and then point 2 at 0, 8, we have this one, and then at point 3 at 6, 5, and then at point 4 at 9, 0. And then these points will be substituted to our equation from the objective functions. So in this case, if our objective function is z equals 2x plus 5y, then we substitute the value of x as 0, and then y as 0 also. So 2 times 0 plus 5 times 0, that is 0. And then for this case, we substitute the value of x here as 0, and then y as 8. That means 2 times 0 equals 0 plus 5 times 8, that is 40. So we have here 40. For this case, 2 times 6, 12, plus 5 times 5, 25. So 12 plus 25, that is equivalent to 37. And then after we identify the values here for our objective function, we have to identify what will be our maximum value. So if this is our maximum value, then this will be the values of, let's say, the values of x and y that we have in our feasible region as our possible solution. Another graphical method is this one. We have three lines equations. So we have this one, another line equation, and then another line equation. And then bounded by these three lines is now what we call as the feasible region. That is highlighted in blue color. Okay. So this time, we will proceed to our example for a linear programming problem. Okay, so this is in the case of in a production plan. So we have here Energy Savers Incorporated produces heaters of type S and L. The wholesale price is $40 per heater for S and $88 for L. Two time constraints results from the use of two machines M1 and M2. On M1, one needs 2 minutes for an S heater and 8 minutes for an L heaters. On M sub 2, one needs 5 minutes for an S heater and 2 minutes for an L heater. Determine the production figures X and Y for S and L, respectively. This denotes the number of heaters and produced per hour so that the hourly revenue is maximized. So it is very clear here. Our objective function is to determine the production figures X and Y so that the hourly revenue is maximized. So we're going to maximize the hourly revenue. So when you read problems in linear programming, usually it's a long paragraph, okay? And then in order to understand or solve the problem, you have to understand what the content or what the paragraph or what the problem is all about. When you have read the paragraph in the first time, of course, definitely you will not understand immediately. So you need to reread the paragraph, okay, or reread the problem. So again, we will read again the problem. Energy Savers Incorporated produces heaters of type S and L. So in other words, we need to, the Energy Savers produce heaters of type S and L. So that means we have two types of heater to produce. So to visualize the problem, we have here our S heaters and then L heaters. Okay, the wholesale price is $40 per heater or for S and $88 for L. So this S, we have here $40 and then $88 for L. So we have here $88 for L. So this is how, or this is the price of each heater. Two time constraints results from the use of two machines M1 and M sub 2. On M1, one needs 2 minutes for an S heater and 8 minutes for an L heater. So in other words, we use two machines in order to produce these products, machine 1 and machine 2. For machine 1, okay, M1, one needs 2 minutes for an S heater and 8 minutes for an L heaters. On machine 2, that means these heaters will pass in machine 1 and in machine 2. On M2, one needs 5 minutes for an S heater and 2 minutes for an L heater. Determine the production figure X and Y for S and L, respectively, so that the hourly revenue is maximize. So we have here our heater, and then our target now is to compute the hourly revenue when it is maximized. Okay, So I mean, we are going to determine the number of your S heater and L heater in order to produce an hourly revenue, which is to be maximized. Okay, so we write our variable. Let's say S here. We use X and Y as our S and L. So our S is in X and then our Y is in L. I mean, sorry for that. Okay. Our L is in terms of Y. We declare this one as our variable. And then we also have here revenue. So we'll make use of revenue R as our revenue. Okay. This time, we will now write our data here for our solution. So we have our machine. Let's say machines. Okay. M1. We have here M1 and then M2. And then we also have the type of heaters. So we have here the type of heaters. So we have our S type. We use X as our variable and then L as our variable Y. Okay, so take note, we have here our types of heaters. So we have this one. And then, of course, on M1, one needs 2 minutes for an S heater. So an M1, this S heaters is 2 minutes to produce. To produce S heaters, we need 2 minutes. And then 8 minutes for an L heater. So we have your 8 minutes. For M2 or machine 2, one needs 5 minutes for an S heater. So we have your 5 minutes. And then we also have 2 minutes for an L. So we have your 2 minutes. Okay. Now take note that our production time, we have here the production time. Okay, or the period when we produce this one. For M1, take note we have here determine the production figure of X and Y. We have this one so that the hourly revenue is maximized. So our production now is based on an hourly basis. So we have 60 minutes. So make sure that you have the same units. Okay. So this time we will now write our objective functions. We write now our variable. We make use of X, Y, and then R. So our objective functions, I will write here objective function. Objective function. Okay, so let me do it again. For the function, our objective function, we have R as our revenue, which is equivalent to $40 per heater for S. So we will multiply 40 times X, plus, of course, this is now our revenue. Okay. So if we sell our product X, we multiply it by 40 plus 88 for Y, for L. So we have here 88 times Y. Okay, so this will be our objective function. This time, we will now write our constraints. Okay. The constraints now is based on the given data here. So for M1, okay, the time for producing this product in machine 1, we have here 2 minutes. So 2 times x, that is 2 minutes for S type, plus 8 minutes for Y type of heater. So we have here 8Y. And then the production time is per hour. So we will make use of less than or equal to. We usually use less than or equal to or greater than or equal to. But this one, since this is hourly basis, so we have here less than or equal to. That is 60 minutes. Make sure that the unit here are the same. Okay, that is for machine 1. Production time for machine 1. For production time in machine 2, we have here 5 times x plus 2 times y, that is less than or equal to, again, 60 minutes. Now, we have already our constraints. How about our data or the non-negativity constraints? Take note of this one. Okay, let me recall this one. Part of our components, I mean the four basic components of linear programming, we have the objective functions, constraints, and then the non-negativity constraints or the data. So we have this one. Okay, so objective functions, constraints, and then our non-negativity constraints we have here, since we want to produce X and Y, or the S type of heater and the L type of heater. So we will write here X, we can make use of X and Y. Okay, must be greater than. Okay, so let me change this one. So X and Y must be greater than or equal to 0. So these are now our presentation for objective functions constraints and our the non-negativity constraints. This time, we will compute this one using a graphical method. Okay, so allow me first to transfer this one here. Okay, so I will just transfer this one here. Okay. So when we graph, because we're doing here graphical method. Okay, so when we graph an equation, we have to make use of these two equations based from this problem. Okay, so for this equation 2x plus 8y, take note when we do the computation, instead of writing less than or equal to, we make use of equal. So equal sign. So we have this equation 2x plus 8y. So for okay, for 2x plus 8y plus 8y, which is equal to 60. So assume the values of x and y as 0. So when x is equal to 0, we have this one. Substitute the value of x as 0. So 2 times 0 equals 0 plus 8y. So that when you compute 8y, that means we have here 2 times 0, the value of x as 0, plus 8y, which is equivalent to 60. So that 8y here is equivalent to 60, and then y is equivalent to 60 over 8, which is equivalent to, when we calculate 60 over 8, that is equivalent to, so using your calculator, so I will be using my calculator here. Okay, 60 divided by 8, that is equivalent to 7.5. Okay, so 7.5. So this is 7.5. This time, we will assume the values of y as 0. After we assume the value of x as 0, we have found the value of y as 7.5. This time, we assume the values of y as 0. So when we assume the values of y as 0, then we will substitute it to our equation. We have 2x plus 8y is equivalent to 60. So that 2x plus 8 times 0 equals 60. So this will be equal to 0. So 2x is equal to 60, and then x is equal to, sorry for that. Okay, I will rewrite it again. I will rewrite it. So we have here x is equivalent to 60 over 2, that is equivalent to 30. So we have the values of x. When we substitute the value of y as 0, then the x equals 30. Okay. That is for equation 2x plus 8y equals 60. Now this time, we will proceed to another equation. We have for 5x plus 2y, which is less than or equal to, we will make use of equal to 60. So again, we will make use of our x and y as 0. So when x is equal to 0, when x is equal to y, that is the first step that we compute our, to identify the other value of the other variable. So when x equals 0, so we have here 5x plus 2y is equal to 60. Okay, so when we substitute the value of x as 0, so we have here 5 times 0 plus 2y is equal to 60. So that y is equal to 60 over 2. That is equivalent to 30. So we will have here the value of y as 30. This time when y is equal to 0, so we have 5x plus 2 times 0 is equal to 60. So this is 0, so we have 5x is equal to 60. So that x is equal to 60 over 5, that is equivalent to 12. So we will write here 12 as our value of x. This time, we will draw our graph. We have our x and our y. They are all positive. So we have here our x and then our y. Okay, so let me write again my line here. Okay. So 30. So we will make this one as 5, 10, 15, 20, 25, 30. So we have here 5, 10, 15, 20, 25, 30. Okay. So we have here 30. This is by 5. And then this one is also by 5. We have here 5, 10, 15, 20, 25, 30. Okay. 5, 10, 15, 20, 25. So with this one, 5, 10, 15, 20, 25. Okay, for the first graph, when x equals 0, y equals 7.5. So when this is our x, take note, this is our x, this is our y. When x is equal to 0, we have this one, and then y equals 7.5, so estimated at this point. And then the other one, when y equals 0, x equals 30. This is our y. When y equals 0, we have this one, and x equals 30, we have this one. So we will draw a line here connecting the 2 points. Okay. That is now our equation, first equation, to this one. Okay. This equation. Another one is the second equation, 5x plus 2y equals 60. When x is equal to 0, y equals 30. So we have when x equals 0, y equals 30. So we have this point. And then the other one, when y equals 0, so this is our y going downward, 0. X equals 12, 5, 10, 12. So probably this is the point. And then this time we will connect the 2 points. Okay. So this is just an estimate. Okay. So this point, this line, this is an equation of your 5x plus 2y less than or equal to 60. So that is our graph. Okay. Now, for the area found here, take note this is less than or equal to 60. So, if we say less than, this is on this, for this value, that means this is our maximum. So, this part will be less than. For this line, of course, less than. So, this part will be less than. And then, of course, this is enclosed by this area. I mean, we have our area enclosed by these two lines. We have this one as the area. So basically, we determine our point as this one, and then this intersection, and then this one, and then of course this point 0, 0 for this part. So we will be calling this part as point A, B, C, D. So it's up to you what variable you're going to make use. So we will call this one as A, point A, point B, point C, and then point D. Okay, so we have 4 points. For point A, of course, that is this point is already located. We found this one as point A. Okay, so I will write here our point A. Point A is located at 0.7.5. We have this one, 0.7.5. Our x here is 0 and then 7.5. For point B, our point here, of course, we do not know. So later on, we will solve this one. How about point C? We have point C, our x here. We have y equals 0 for this line. Y equals 0, x equals 12. So for point C, y equals 0 and then x equals 12. That is our point. And then point D, of course, from the origin, that is 0, 0. So how do we find the value of B? Of course, we have to combine these two line equation. Okay? So to compute that one, allow me to utilize this area. Okay. Let me check. Okay, so from this part, we will compute point B. So this is an intersection of two lines. So we have to combine two lines. We have the equation of two lines, 2x plus 8y. That is less than or equal to, when we compute, we will make use of equal to, and then we have here 5x. Okay, so we have here 5x plus 2y, which is equivalent to 60. So we will be using determinants for this case so that we can find the value of x and y. We combine the two equations. So in determinants, you have here, using their augmented matrix, we have 2, 5, 8, and then 2, which is equivalent to 60, 60. So we will be using determinants to solve the values of x and y, so that when we solve the value of x, that is equivalent to 2 times 2, that is 4. No, that is not our solution, but I will rewrite it again. Okay, so 60, 60, and then we have here 8, and then 2. The denominator is 2, 5, 8, 2. Okay, so that when we compute this one, 60 times 2, that is 120, minus 8 times 6, 48, 480, divided by 2 times 2, that is 4, minus 8 times 5, that is 40. So that is equivalent to 120 minus 480, that is 360, negative 360 over 40, 36, negative 36. So that is equivalent to 10. So we have the value of x as 10. How about the value of y? So y here is 25 and then 60, 60. Okay, the denominator is, we have negative 36. So that is equivalent to 2 times 60, that is 120. 2 times 60, 120 minus 60 times 5, 5 times 6, 30, 300. Divided by negative 36. Okay, so that is equivalent to 300, negative 300, 120. So we will compute this one using calculator. 120 minus 300. So that is 180 equals divided by negative 36. So it is equivalent to 5. The value here is 5. Which means our x is 10 and y is 5 for this intersection. So our b is x equals 10 and y equals 5. Okay, so we have here the values of points A, B, C, D. This time, this value, okay, we will be using this one in our computation of revenue. So we have our revenue. I will write here our revenue, which is equivalent to 40x plus 88y. So for point A, I will write here point A, which is 07.5. The revenue is 40 times 0. We will substitute the value of x and y plus 88 times 7.5. The equivalent is, so we will be using calculator again, 88 times 7.5, that is equivalent to 660. For point B, wherein we have here 10, 5, our revenue is 40 times 10 plus 88 times 5. So when we compute this one, our value is for 10, 5, that is using calculator, that is 840. Okay. For point C, that is 012, our revenue is equivalent to 40 times 0 plus 88 times 12. So using a calculator, that is 88 times 12. Okay, 88 times 12. C, I think C here is X. Sorry for this one. Our X is, we have here, our X is supposed to be 12. And then Y is equal to 0. So we have an error for this part. This is supposed to be 12. So 40 times 12 plus 88 times 0. So that is equivalent to 40 times 12, that is 480. Okay, for points D, we have here 0, 0. Definitely, there is no revenue for this one. So if you have noticed, the maximum revenue is 840 for this case. Therefore, this will be our solution, this one. Our final answer is we are going to produce the X, our S heater as 10. So we will make use of S equals 10, and then L is equivalent to 5. That means we're going to produce this type of heater. For S type, we have 10, and for L type, we have 5. In order to maximize our profit, per hour, which is equivalent to 840. So this is an example of a maximization. We maximize our profit by producing 10 S type of heater and 5 L type of heater.